Today, we are going to get into the nitty-gritty of a battery technology that could really, truly change our entire energy landscape, and that is sodium ion. So let's just dive right in. Think about it for a second. Your phone, your laptop, maybe even your car, the entire power grid that keeps our lights on, pretty much everything in our high-tech lives runs on lithium-ion batteries. But as our hunger for energy just keeps growing and growing, we have to ask a pretty serious question. What are we going to do when there just isn't enough lithium to go around?
All right, so let's start right there with the big challenge we're all facing. I mean, don't get me wrong, lithium-ion batteries have been absolutely revolutionary, but their total dominance has come with a pretty steep price tag, both in dollars and, in global politics.
Let's just break that down a bit. First off, lithium is, well, it's rare, and it's only found in a few specific places on the planet, which creates all this geopolitical tension and really, really fragile supply chains. So naturally, as demand just skyrockets, so does the cost. And that creates a massive bottleneck for the green energy future we're all trying to build. This really puts it all into perspective. Just look at that difference in abundance. Lithium makes up this tiny, tiny fraction of the Earth's crust, 0.0017%. Meanwhile, sodium? It's sitting there at 2.3%. That means sodium is over 1,300 times more abundant. It's literally everywhere. It's in the oceans, it's in the ground, it's in the salt on your kitchen table.
And that just staggering difference in availability brings us to what might be the most promising alternative. One that honestly has been hiding in plain sight this whole time: sodium.
The case for sodium is just incredibly strong. It's cheap, you can get it almost anywhere, and because it sits right below lithium on the periodic table, its chemical properties are super similar. That makes it, at least on paper, a fantastic replacement. On top of all that, it even offers some bonus perks like it's more stable at different temperatures and it's safer. Those are huge wins for energy storage. And check this out. This is one of those brilliant, practical advantages you find in manufacturing. In a lithium battery, you're forced to use expensive copper foil for the anode. But with sodium, it doesn't have that same corrosive reaction with aluminum. So what does that mean? It means you can use cheap, standard aluminum foil for both sides of the battery. That is a massive cost saver, and it means we can use a lot of the same manufacturing lines we already have.
So it sounds perfect, right? Abundant, cheap, safe. It seems like a no-brainer. But of course, it's never that simple. Scientists and engineers very quickly ran into a very, very big problem, which, ironically, was also a very, very small problem.
34%. What in the world does that mean? Well, that's how much larger a single sodium ion is compared to a lithium ion. Now, that might not sound like a lot to you and me, but in the microscopic world of electrochemistry, that is a colossal difference.
And believe me, that size difference isn't just some academic detail. It has very real, very destructive consequences. This image here shows you exactly what happens when you try to use the standard anode material, graphite. You're trying to force those bigger sodium ions into a space designed for tiny lithium ions. The constant stress of shoving that bigger ion into a small space causes the material to crack, to crumble. It just gets pulverized. The battery literally tears itself apart from the inside out. And this is the crucial point. This physical breakdown causes a total cascade of performance failures. You get slower charging, lower overall capacity, and just terrible long-term stability. All of a sudden, that simple, abundant solution became a really complex and difficult engineering puzzle. If graphite, the industry standard, wasn't going to work, then what would?
And this is where the hero of our story enters the picture. The solution, it turns out, wasn't something neat and tidy. It was something messy, disorganized, and absolutely perfect for the job, a material called hard carbon.
Okay, the best way to explain the difference is with an analogy. Think of graphite like a perfectly organized parking garage. It has tight, uniform spaces, all designed for compact cars. That's our lithium. Now, if you try to park a giant SUV, our bigger sodium ion, it just won't fit. You'll scrape the sides, cause damage. But hard carbon? That's more like an open parking lot with all sorts of flexible, varied spacing. Its messy, disordered structure has all these larger gaps between its layers, and it just easily welcomes those bigger sodium ions right in.
And we can actually see this difference in the scientific data. This is what's called an X-ray diffraction pattern. See that sharp, narrow peak for graphite? That tells scientists it has a highly ordered, very neat and tidy structure. Now look at hard carbon. Its pattern is just this broad, gentle hump. That's the scientific signature of a messy, disordered material. And that messiness is precisely what makes it work so well.
What's really fascinating, though, is that our understanding of how hard carbon actually works has evolved over time. You can see from this timeline of research here, scientists first thought it was a pretty simple process. But now we know it's a much more sophisticated, multi-stage mechanism that really explains why this material is so uniquely effective.
It's kind of like a three-step dance. First, the sodium ions stick to the surface, that's adsorption. Next, they slide in between the carbon layers, that's intercalation. And finally, they fill up all the tiny nanopores inside the material itself. This combination, adsorption, intercalation, and pore filling, is the secret sauce. It's what gives hard carbon both its high capacity and its great stability.
But the story doesn't stop there. Innovation never does, right? With hard carbon pretty much established as the go-to material for the anode, researchers are now pushing the boundaries even further, trying to squeeze even more performance out of it.
And this brings us to the next generation, these so-called anodeless or hybrid designs. The concept here is just brilliant. You use the hard carbon to do its normal three-step dance, but then you push it just a little bit harder, which causes a super thin, uniform layer of pure sodium metal to plate right onto the anode surface. And this graph shows you exactly what happens. You can see the initial capacity you get from the normal hard carbon process, and then you see a second, massive jump in capacity when that sodium plating kicks in. This hybrid mechanism basically multiplies the storage capacity, giving you a huge leap in the battery's overall energy density.
This hybrid approach can boost the energy density by up to 25%. And that starts to bring sodium-ion batteries into direct competition with traditional lithium-ion batteries on performance. But you still get all those amazing advantages of low cost and abundance. Now, the main challenge is making sure that plating process happens safely, without forming these dangerous spikes called dendrites that can cause short circuits.
Which, brings us right back to the big picture. We started with this huge problem of scarcity and cost with lithium. We found this incredibly abundant solution in sodium. We overcame a fundamental science problem with a clever, messy material. And now we're pushing that solution to the point where it can compete on performance. All the pieces are falling into place. The only question left is, how quickly is this revolution going to unfold?